Ellis of Groq is going to talk to us about his construction or his new library on effects called Bluefin. Tom, you have the floor.
Thanks very much. Yes, my name is Tom Ellis. I've developed a library called Bluefin, and I'm going to give you an experience report of using that in production. So what is Bluefin? Bluefin is an effect system for Haskell. What is an effect system? Well, an effect system is a library for giving you access to a variety of effects. What is an effect? Well, that's a very good question, but at the very least it contains these effects: state, exceptions, I/O, streaming, and perhaps many others. And an important property of an effect system is that it delimits the scope of effects. So you can see where effects may or may not happen within your program. From a functional architecture point of view, what does this look like? Well, we like to design our programs as a collection of loosely coupled components interacting in well-defined ways. That's our holy grail of architecture. How does Bluefin help here? Well, Bluefin is an FP solution to this problem. So in the FP world, components are just functions. And loosely coupled means that there are few dependencies between these functions. And well-defined interactions, well, the interactions we have between our functions, between any components of our program, arise ultimately from applying functions to arguments. And the arguments that we get to apply to these functions were just the results of other functions. And in a typed FP world, everything is well typed, so we can make invalid states representable. That is to say, we can ensure that only certain interactions are possible between various components of our program. In the Haskell world, the venerable effect system is called MTL. And in the MTL world, you passed effects at the type level. So if you wanted a component that performs an error effect, a sort of an exception-like effect, you would have a monad error constraint at the type level. Same for state. If you want to manipulate a state of type ST, you incur a monad state constraint on the definition of your function. Now, a modern effect system in Haskell, or a recently developed one, Effectful, takes a similar approach. If you want to be able to raise an error of type EX, well, you have a constraint at the type level that allows you to raise that error, and similarly for manipulating a state of type ST. Now, Bluefin takes a different approach. In Bluefin, the ability to use an exception effect is represented by a value level argument called exception. This is sort of an exception handle or a capability to throw an exception. In order to manipulate a state of type ST, you take something at the value level. This is a lot like, for example, an ST-ref or an IO-ref in Haskell. It's a state ref that you can manipulate within your operation. So Bluefin and Effectful are very similar, but they have this difference in terms of how they take effects, or how effects are passed into a function. These are both called actually IO wrapper effect systems, which is something I want to touch on very briefly because it's, I'll say without going into much more detail, it allows predictable performance and it allows resource safety, and that differs from the older effect systems like MTL. But I won't say much more about that here. So what's the difference between constraints and arguments from a practical point of view? Well, my hypothesis is that passing effect handles as arguments will reduce the practical amount of coupling that you see in your program. The challenge that I get in response is that passing effect handles will get very tedious. If you have many effects in scope and you have to pass them as arguments, well, you don't really want to do that. You just want to infer them from the environment. There is a problem with inferring them from the environment, and that is that you get worse type inference. You kind of have to cross your fingers and hope that the constraints can be inferred. And if they can't, you have to do a lot of plumbing manually, which is much worse than just passing arguments. And in addition, you can only have one effect of any type in scope at once. So you can only have one state int effect in scope at once. What happens if you want to manipulate two ints? Well, you just simply can't. So what does my anecdotal evidence say? Well, my anecdotal evidence bears out that I was correct. Well, I'm the developer of Bluefin, so take that with a big pinch of salt. But I like passing these handle arguments as values. And I haven't found that it gets tedious at all. In practice, what do we see? Well, I really have mostly up to 3 effects in scope in any given effectful operation. Sometimes I might have as many as 5 effects in scope, but that's quite rare. And normally, if I was getting a lot of effects in scope, I would simply bundle them up into a product type like we would do for any 2 or more data values that often occur together in our program, put them in a tuple, put them in a record, and pass them around together. So my experience has been in developing a compiler-like implementation, very straightforward conceptually, and we all know and love it. We take some text source, you do a variety of manipulations on the AST that you pass from the text source, each of which may have its own state that you manipulate during that transformation process, and in the end you get machine code out. I found in this kind of problem that effects were not that useful. It's a sort of one and done program. You run the program and it's either correct and you get a result out, or it fails. And you don't really need to handle effects in a sophisticated way in this kind of program. If I was writing a long-lived server program, for example, well, I think it would be very important to be able to handle effects, recover from handle exceptions, recover from thrown exceptions in client code, and continue processing. But in a compiler, that I've found that to be less useful, so I haven't got so much value out of that. We do a lot of state manipulations, of course, but even that hasn't proved to be tremendously more useful, because we can just use the standard Haskell pattern of state threading, passing around a state value into a function and the new value out of the function. What I have found, and what surprised me a lot, is that streams are extremely useful. And a stream is where you can yield values of a type from your operation for processing elsewhere. How would you normally do that in Haskell? Well, in order to return a sequence of values from a function, you'd return a list. So this is how you do it in the list monad in Haskell. Here we're iterating through the values of 1 to m and binding them to I, then 1 to n and binding them to j. We enforce some condition on I and j, and then from this function f we yield yet more results based on the values of I and j. So that's what happens in the list monad. In a streaming system, what you do is you do 2 nested for loops, and then you check the condition using when, and then you run an effectful function which can yield yet more values to this stream. If you want to add another effect in this streaming setup, that's very easy. So if I want to do a logging operation, then I just add the logging operation, no problem. That's just another operation in the do block. If you want to do that in a list monad setup, well, you just can't. I mean, there's nothing you can put here to do that. So it doesn't support that. So effect systems, or the streaming provided by effect systems, allows mixing effects in this way, whereas the list monad doesn't. Now here is a short example. In this function squares, I am yielding to a stream the square numbers between 1 and n. So I take numbers from 1 to n, I square them, and I yield them. So this produces a sequence of integers. The sum function now takes a stream as an argument, or well, an effectful function which produces the sequence of results. And then it accumulates into some state, starting from 0, all the values of that stream. So what's it doing? It's summing all the values of that stream. And this is what it looks like to combine them. We just compose those operations and run them. So this is a separation of concerns. I can define the function that produces values separately from the function that consumes values. And in fact, I think if we interpret streams as a form of dependency injection, it's easy to then understand why they're such a powerful architectural tool. So the underlying implementation of stream is that it's just a function that accepts a stream handle to A. It's just a function that accepts a value of type A and then does something with it. And what is done with it is deferred. It's a deferred choice that's deferred to this for each block, where you instantiate this functional value with the actual operation that it performs. And in fact, I have a general version called coroutine that not only accepts an A and processes it, but then returns a value of type B. And this is literally, well, a function that accepts this coroutine handle is literally a higher order function. And then we defer until later the instantiation of that operation. So this is literally a form of dependency injection. It's a sort of well-scoped form of dependency injection. Now, I've been converting our code base piecemeal. It started off as a mixture of MTL and transformers, concrete transformers. And I've been converting it bit by bit to Bluefin as the need arose. And I've actually found this very straightforward. So MTL and transformers are kind of interconvertible fairly straightforwardly themselves. And the constraints that the MTL world provides can actually be instantiated by Bluefin constraints. So we can interpret monad error and monad state as Bluefin operations that take these exception and state handles. And similarly, it's straightforward to handle concrete monad transformers and then reinterpret them as Bluefin operations. We can also go backwards. If you have a Bluefin operation, you can handle the Bluefin operation and then reinterpret it as a concrete monad transformer, and then you can go back to MTL. I have not implemented a direct route back to MTL, but that's kind of work in progress in Bluefin, and I'll add that if that proves useful. This is only kind of useful in a legacy environment where you're working with code written in an existing form, but it's very nice to know that that does work out straightforwardly. So finally, to sum up, what are effect systems from a functional architecture point of view? Well, I said it's about defining your program as a collection of components, which are functions that are loosely coupled together. So there are few dependencies between those functions, and that they have well-defined interactions through applying functions to arguments. And in a typed world, these arguments can be well typed in order to rule out certain sorts of behavior. And Bluefin just extends this to the effect systems world. So Bluefin effectful operations are functions, as we expect from any sort of monadic Haskell setup, but not just the data arguments or data values in your program are arguments, also the effect handles are arguments. What does this give us? Well, it gives us better type inference. And once we have better type inference, we can take streaming seriously, because streams are rather difficult to use in this implicit type level parsing setup. And once you can take streams seriously, then you have this wonderful separation of concerns or dependency injection kind of setup, where you have a very nice way to break your program up into these communicating components. So I'd sum up Bluefin as saying it's a lower friction approach to existing architectural best practice. So if you're interested in finding out more about Bluefin, well, you can check out some of the resources here. Firstly, if you want to ask me a question, you are welcome to open an issue on the Bluefin GitHub repo. And I have also collected together a number of resources, talks and articles about Bluefin, if you'd like to read or watch anything more there. So you're welcome to do that. So that's all from me for now, and if there's time, I'll take any Q&A.
Okay, let's go ahead and thank our speakers. Tom, we have plenty of time, so is there any questions? You're also, oh, Andrea.
The quote there is a functional call imperative shell, and sometimes when looking at effect systems, I feel like we're putting the imperative back everywhere. We track them. The effect system help us track them either on types or on the arguments. But I still, I would be putting imperative and state back everywhere. Do you want, does that make sense? Is that a question?
Is that a question?
I mean, like in terms of best practices in functional architecture, right? That's the last what you said in the last slide. Is it putting effects and not restricting where you put effects? So putting effects everywhere, is that a good thing or is that a bad thing?
So perhaps controversially, I would say I don't have a problem with imperative programming per se. And I would say that Bluefin allows you to write in an imperative style. But even Simon PJ famously said Haskell is the world's best imperative programming language. I think we should embrace that where it makes sense. What we really value from the functional world is making invalid states unrepresentable. And I would extend that and say, make invalid behaviors unrepresentable. So what Bluefin and effect systems in general do is they allow you to circumscribe the range of effects that may occur in any given context, and that is what we want. It's not that we should eschew imperative programming per se, but what we want to avoid is unrestrained imperative programming, where we can mutate anything in any location, where we can throw an exception anywhere. That's what we want to avoid. So I would say the best parts of functional programming, from the point of view of design and architecture, is the ability to enforce these well-defined interactions, and that comes from making invalid behaviors unrepresentable.
Thank you.
Any other questions? Yeah, I have a question. So you said the magic words that the performance is predictable, and that piques my interest. So I am wondering if you have measured any kind of program that uses Bluefin when you're passing, like say 1 or 2 effects versus when you're passing more than 7. And I'm specifically curious about this because I know that GHC has, I think, or generates different calling conventions when there's many arguments to a function. So that should intersect with the design of Bluefin, because in extreme cases where you have lots of effects, I think you will now have a slower calling convention.
That makes sense to me, yes. I haven't benchmarked that specifically. What I mean about the predictable performance, I don't necessarily mean good performance, actually, but I do mean predictable. And I can clarify or explain more about that. The baseline for comparison would be MTL and monad transformers, where underlying that, you are building your effects up from data types, algebraic data types, and then interpreting those data types, deconstructing them at a later stage. That's actually extremely high performance when everything can be inlined. So when GHC can see your whole program, it will actually avoid constructing and deconstructing these data types, these values. When everything cannot be inlined, well, then you've got a big problem, because you're doing a lot of very slow work in one module, and then undoing the work and interpreting it as some operations in another module. And that leads to well, a big slowdown, but even worse, it's unpredictable. Its performance depends on very subtle behaviors of the GHC optimizer. So these IO-based effect systems, of which Effectful was the first one, don't have that problem, because underlying them, they're only ever performing IO operations. So state is an IO ref under the hood, and an exception is just a GHC RTS exception. So that's predictable. It doesn't depend on any subtleties of the GHC optimizer. Now, in practice, they should be also should be well performing. I mean, they should work as well as any other IO code in Haskell. But with regards to passing the number of arguments, I haven't done any specific benchmarks on that.
Okay. We have two more questions. You had your hand up first. Do you want to say your name?
Matthias.
Matthias.
Matthias Gergens. Hi, John. Does this at all relate to session types? Like, because session types were a bit more popular like 10 years ago or so. Does it have anything to do with it? Can you
Hi, Matthias. So not directly, but an extension of Bluefin could do that. It's something I'd be very interested in implementing. For session types, you really need to work with linear types, and Haskell GHC now does have linear types. One very interesting way you could deal with that is you could have two communicating components that can detect the state of the other, essentially. So you could process a stream and detect, process an upstream stream of values and detect termination of that stream. Or you could detect the moment at which a stream stops yielding values of one type and starts yielding values of another type. So that would be an example of a typed session. And I have some experiments with that, and I think it is possible with Bluefin, and it's possible using GHC's linear types implementation. But there are a number of ergonomic problems, a number of rough edges with GHC's linear types implementation. So I haven't really pursued that much further.
Yeah, hi, this is Gary. So my question is, so as far as architectural concerns, and in your talk as well, you talked about the interface to Bluefin, right? Like, what does it look like to use Bluefin? But now, when it came to performance, you also mentioned that it's an important piece of the puzzle that this is like this IO-based like at the bedrock, you have IO-based handlers for the various effects instead of the MTL-style data types. How closely coupled are these two things? Like, could you have, and would it work well if you had a Bluefin that didn't use this IO-based representation for use cases where I can't have IO at the base of my stack? For example, if I'm writing hardware and I want to use an effect system to describe parts of my circuit, but I actually want to or need to eventually get rid of everything that is not just pure stuff.
Good question. So the short answer is you can do something like that. You can add a Bluefin API over a different implementation. The longer answer is that if you try to do that, you will get into a lot of trouble with GHC's, the way GHC handles these constraints. The only way to get the effect tagging that Bluefin uses to make sure effects can't escape their scope to work out in current versions of GHC is to have what's called an incoherent instance. And that works fine in this particular case, of the particular case where Bluefin is implemented as IO under the hood. If you try to use that to implement a version of Bluefin that uses, say, transformers under the hood, then everything looks like it works. But I think these incoherent instances then end up sending, or can end up sending, an effect to the wrong place. It can send them to the place of another effect that has exactly the same type, but isn't where you intended to send it.
Oh, because the GHC specializer gets confused, you mean?
I don't think it's to do with specialization specifically. It's to do with how incoherent instances are resolved. And it is that's a very gnarly problem. It's kind of lucky that it works out well, successfully in the way that it does for Bluefin. And that's just a sort of coincidence to do with how the underlying implementation works. Now, in theory, GHC could implement something like set types, type level set types, and then Bluefin could use that and there wouldn't be a problem. GHC would just do the right thing. But as things are, I've kind of hacked type level set types into GHC in this way using incoherent instances, and they work by coincidence, but it makes it hard to extend to other cases.
Any last questions?